Welcome to this explainer, everyone. Today we're going to unpack something pretty fascinating. It's the invisible math that actually governs our daily lives. Every time you make a choice, set up a schedule, or, organize your desk, you're literally interacting with the profound rules of probability and combinatorics. Now, don't let those big academic words scare you off. We are absolutely not going to look at these as boring textbook equations. Instead, think of them as empowering mental tools. By the end of this, you're going to look at every single choice you make through a totally different, mathematically illuminated lens.
Okay, let's dive into this. Picture this. You're at the track, and 8 horses are lined up right there at the starting gate. Assuming there are absolutely no ties, how many different ways could those 8 horses finish the race? What do you think? Maybe a few hundred? A couple thousand? Just kind of keep that scenario in the back of your mind for a minute, because as we build up our mathematical toolkit today, we're going to uncover the exact answer. And let me tell you, it is a massive number. It perfectly shows just how explosive possibilities can really be.
To get there, we're going on a nice, logical, step-by-step journey. We'll quickly cover the universe of sets, operations, and intersections, the rule of counting, permutations, and combinations. Don't worry, we're scaling up from the basics, so we definitely won't leave you behind. Let's get right into it.
All right, Section 1, the universe of sets.
We're starting right at the absolute bedrock of probability, and that is set theory. In math, a set is honestly just a collection of well-defined things. It could be, say, all positive integers, or simply the vowels in the alphabet. Grasping sets is absolutely crucial because they basically define our whole universe of options before we even start making choices. And this brilliantly illustrates how different possibilities are grouped within a larger universe. See that large box? That's our universe. Inside it, we've got a set, and totally tucked inside that one is a smaller subset. If every single element of the smaller set is also in the bigger one, then it's a subset. It's like saying the smallest circle is thin brown hens, the middle one is all hens, and the big box is the whole shebang, all chickens. Recognizing these nested setups is our very first tool for organizing reality.
Moving on to Section 2, operations and intersections.
Right. So now that we know how to group things, we need to see what happens when these sets interact. Because let's face it, in the real world, categories almost never exist in perfect isolation. They overlap, they mix, and sometimes they totally exclude each other. Looking here, we have the union of two sets. That's literally everything in both circles combined. The union is our OR scenario. It's an outcome where one thing happens, or the other happens, or both. Then we have the intersection. This is the AND scenario, shown by just that overlapping bit right in the middle. The intersection means both things have to happen at the exact same time. Being able to visualize these abstract terms is a real game changer for counting outcomes accurately.
And this brings us to our really vital rule, the Inclusion-Exclusion Principle. Basically, to find the true total of a union, you add up the items in your first set, add the items in your second set, but then you absolutely have to subtract the intersection. Now, why does this matter to you? Well, think about it. If you count everyone who likes apples, and then you count everyone who likes oranges, the folks who like both just got counted twice. Subtracting that overlap makes sure your real-world counting is spot on.
Which brings us to Section 3, the rule of counting.
Okay, so we've grouped sets and we've handled the overlaps. But what happens when we start making sequences of choices? We transition from just organizing sets to actually multiplying outcomes. This is our core branching tool. Now, when the choices are small, we can visually map them out with a tree diagram. Imagine a super relatable choice, packing for a trip. You've got 3 shirts, red, blue, yellow, and 2 pairs of pants, tan and gray. From a starting point, you just draw 3 branches for the shirts. From the end of each shirt branch, draw 2 more for the pants. Boom! Instantly, you can trace the lines and see you have exactly 6 different outfit combinations. Pretty simple, right? But trees kind of only stay manageable when the options are small. Let's move to and see how this builds into the fundamental principle of counting. If an experiment has multiple stages, you literally just multiply the number of options at each stage. Let's build a standard license plate, 3 letters followed by 3 digits. Step 1 is picking that first letter. You've got 26 options. Step 2, second letter, another 26, then 26 again. Moving to the digits, it's 10 options, then 10, then 10. Here comes the crazy part. When you multiply 26 by 26 by 26 by 10 by 10 by 10, it explodes into an astonishing 17,576,000 possible license plates. Seriously, let that sink in for a second. Over 17 million. A simple 6-step process generates an unbelievable amount of unique outcomes. It completely proves mathematically how incredibly small choices generate an immense universe of possibilities.
All right, Section 4, Permutations, or when order matters.
So for more advanced sorting, when the exact sequence of your choices makes all the difference, we use a handy little mathematical shorthand called the factorial. It's written with an exclamation point. Remember those 8 horses from the start of our explainer? Finding out how many ways they can finish is an 8-step decision. Any of the 8 can finish first. Then, well, only 7 are left to finish second, 6 for third, and so on, all the way down to 1. That is 8 factorial. Multiply 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and you get exactly 40,320 possible finishing orders. No way, right? Over 40,000?
Now, watch how the environment actually changes the math. Imagine seating people at a dinner table. If you're seating 6 people in a straight line, it's 6 factorial, which gives us 720 ways. But at a circular table, there's really no distinct first or last seat. If everyone shifts 1 seat to the right, it's the exact same arrangement relative to each other. Because of this little quirk, we have to divide by the total number of seats. So 6 people around a circular table actually only have 120 unique seating arrangements, not 720. Kind of a cool trick, honestly.
And finally, Section 5, Combinations, where we're just choosing the group.
Sometimes, you just don't care about the order at all. You only care about who or what actually made it into the group. Think of this as the ultimate showdown for sorting reality's variables. You have to ask yourself one question: does order matter? If you're making a baseball batting lineup or picking a president, vice president, and secretary, the order absolutely matters. Those are permutations. But if you're just picking a 3-person committee for a club, picking person A then person B is exactly the same as picking person B then person A. The order doesn't matter, which means those are combinations. And because of that, the total number of outcomes is going to be way, way smaller.
So, the crucial point is knowing how to apply this to real-world parameters. Let's say you've got a pool of 5 women and 7 men, and you need to form a committee of exactly 2 women and 3 men. Using the combinations formula, which is usually read as n choose k, we first figure out the ways to choose the women. That's 5 choose 2, which gives us 10. Then the men, 7 choose 3, which is 35. We multiply those together, 10 times 35, and we get exactly 350 possible committees, all calculated without ever stressing about who got picked first. And this perfectly leads us to the mathematical awe of Pascal's triangle. This beautiful, cascading triangle of numbers perfectly maps out combination logic and binomial coefficients. It's like a giant puzzle. Every number is just the sum of the 2 numbers directly above it. Amazingly, if you look at the rows, they correspond perfectly to the combinations formula. If you want to know 4 choose 2, you look at the 4th row, go to the 2nd position, and bam, there's your answer, 6. It's a stunning visual proof of the deep, hidden symmetry that underlines all our choices.
We've seen how picking just a few letters and numbers for a license plate explodes into over 17 million outcomes. We've seen how a simple race with 8 horses gives us over 40,000 finishes. So I want to leave you with this provocative thought. Considering the dozens of decisions you make every single day, what to wear, who to talk to, which route to take to work, how many infinite permutations exist in your daily life? You are literally navigating an incredibly vast universe of possibilities every single second. Armed with this mathematical toolkit, you can now truly appreciate the staggering scale of the choices you make. Thank you so much for exploring this with me today.